Good evening, my YouTube viewers. It is Crystal here, and I wanted to do another code review for you. This code review is going to be with Tensorflow, and it's going to be a regression problem. And I got it from the Tensorflow website, but I wanted to go ahead and do a code review on it anyway, even though I got it from the Tensorflow website, because I did make some changes to it. And let's just see what we've got here. I'm not going to rerun the program because it's with Tensorflow, and it does it's a model and it iterates. It has epochs, but I forgot to put printf.version there, and I already know what the version is. It's a version 3.11. So I got this code from the Tensorflow website, but I did actually make a few modifications to it. And I'm going to go ahead and go over the code, and I'm going to make a blog post on what I've gone over as well. So I put it on Google Colab, which is a free online Jupyter notebook hosted by Google. And the thing about Tensorflow is Tensorflow was developed by Google Brain. So Tensorflow is a Google library on top of Google Colab. So it's really interesting. And in the past, I had studied PyTorch, and I found PyTorch very hard to work with. So I'm hoping that Tensorflow will be easier for me to work with. But from what I've heard, Tensorflow has a lot bigger learning curve than sklearn. So I'm assuming that I'm going to be learning Tensorflow for a while, but that's what my plan is, to learn Tensorflow and become adept at it. So after we have created the program, what we're going to do is we're going to import our libraries. So we're going to import matplotlib.pyplot.splt, which is a graphics library. We're going to import NumPy as MP, which performs numerical computations. We're going to import pandas as PD, which does data processing, and we're going to import Seaborn as SNS, which is also a graphics library with statistics in it. And so in order to make NumPy easier to read, it's np.set print options precision equals 3, suppress equals true. And we're also going to import TensorFlow as TF. From TensorFlow, we're going to import Keras. From TensorFlow Keras, we're going to import layers, and then we also can print the version of TensorFlow, which I know it's 2.11. But the thing is I was wasting my time on Kaggle, and the version of TensorFlow on Kaggle is only 2.3, so I can't use a lot of the code on Kaggle that I can use on Google Colab, because Kaggle isn't up to date. And I even put a question in the discussion asking how I can upload the most current version of TensorFlow onto Kaggle, and the reason why is because I tried to do it and it wouldn't work. So we'll just see how we get on. If I can upload the most current version of it, I will, and then I'll do some more work on Kaggle and make some more code reviews on that. So after we have imported our libraries, we're going to load the data set. And we got the data set from the UCI, and then we set the column names, and then raw data set equals pd.read.csv, URL, names equals column names, NA values equals question mark, comment equals \t, sep equals space, and skip initial space equals true. And then we check the raw data set head. So that's the first 5. So you can see we've got MPG, cylinders, displacement, horsepower, weight, acceleration, model year, and then origin. I checked the shape of the data set, and it's 398 rows by 8 columns. We check the size, and you multiply 398 by 8 times 8, and you'll get 3184. And now what we're going to do is copy the data set, so if anything happens to the data set, then you still have a copy of it. So data set equals raw dataset.copy, and then data set tail. So now you can see the last 5 rows of the data set. We're going to check for null values. Under horsepower, we have 6 null values, and so we decided that we were just going to drop any null values. So dataset equals dataset.drop NA, and then dataset shape, we've got 392 over 8, which means we dropped 6 rows. So we're going to analyze the target, and so this is the distribution that the target makes. It's not quite a normal distribution, but that's the distribution that the dataset MPG makes, which is your target. Or now we're going to pre-process the data. So dataset origin equals dataset origin, and then you're going to map it. So 1 is USA, 2 is Europe, 3 is Japan, and so now you can see that it's mapped. So instead of 1, 2, 3, you have USA, Europe, and Japan. And now what we're going to do is we're going to one-hot encode it. So we're going to do dataset equals pd.getDummies, dataset, comma, columns equals origin, prefix is space, prefix sept is space, and then dataset is tail. So now we have one-hot encoded it. So if it is Europe, then it'll get a 1 on Europe and a 0 everywhere else. If it is Japan, it'll get a 1 on Japan and 0 everywhere else. And if it is USA, you'll get a 1 on USA and 0 everywhere else. So that's what they wanted to do, is they wanted to one-hot encode this. You could have just as easily have encoded it, but I guess, I don't know, maybe they felt that they would get a higher level accuracy if they one-hot encoded it. So now what we're going to do is we're going to split the data set up into training and validation sets. And one thing that I just want to point out is they didn't use sklearn to do this, because sklearn has the train test split function, and they didn't use sklearn to split the data set. You won't find any sklearn in this program at all. So train dataset equals dataset.sample, frac equals 0.9, random state equals 0, val dataset equals dataset.drop, train dataset.index. So the training set is 90% and the validation set is 10%. And then you check the shapes. So the train set data set, you have 353 rows by 10 columns, and the validation data set, you have 39 rows by 10 columns. And now we're going to use Seaborn to analyze the data sets. So if you like to analyze things, you can compare these analysis if you want. Now we're going to describe the data set, but we're also going to transpose it. So the statistics are horizontal and the columns are vertical. In MPG, which is the target, is the top one. Now we're going to separate features from the labels. Train features equals train.datasetCopy. Val features equals val and underscore dataset.copy. Train labels equals train features pop MPG. Val labels equals val features pop MPG. So pop is something that is in an inbuilt function in Python, and I normally use drop, but in TensorFlow they wanted to use pop. So what we do is pop takes out the MPG, by the way. So what we want to do is we want to check the shapes. So train features is 353 by 9. Val features is 39 by 9. Train labels is 353. And val labels is 39. So that's interesting the way they did that. And now what we're going to do is we normalize it. And normally, whenever I normalize something, I have a formula that I can use to normalize it. But TensorFlow has its own function on how to normalize things. So we're going to use the TensorFlow's function on how to normalize things. So we're also going to describe it and transpose the mean and the standard deviation. So now TensorFlow has its normalize function. So normalizer equals tf.keras.layers normalization axis equals -1. Normalizer.adapt NP array train features. Print normalizer.mean numpy. So I guess those are all the means there. And that's what how TensorFlow normalizes data. And I'm going to make a blog post on this, and then when I go into make the blog post, I'll go into normalization in TensorFlow in much more depth. So now it says first equals NP array train features, and it's going to be all the rows and the 0 column because it doesn't include 1 with np.print options. Precision equals 2, suppress equals true, print first example first, print normalize, normalizer first numpy. So basically the first example, they're just showing you that's what the mean is, I believe, on the first example. And then they're showing you what the normalized is. And so basically this information is normalized. And I think that what they're doing is they're using the mean and the standard deviation to do that. And that is why they showed you the mean and the standard deviation in the description. But whenever I do my blog post, I'm going to explain how normalization works. And so that'll be good if you want to know how normalization works. But I know that it works on the mean and the standard deviation, and that's why they included mean and standard deviation in the when you describe it. So now we're going to do a DNN, which is a deep neural network. So we're going to build and compile our model. So def build and compile model norm. And so model equals keras.sequential norm, comma, so that's the normalized data. Layers.dent64 activation equals relu. Layers.dent64 activation equals relu. Layers.dents1. And let's just see. So normalizer first numpy. And they call it norm. And then model compile loss equals mean absolute error. Optimizer equals tf.keras.optimizers.atom. And then 0.001 is your learning rate. So now we built our model. And so now it says DNN model equals build and compile model normalizer. So that means it's going to put the normalizer in there. And DNN summary, and so that's a summary of the model that you can see. And now what we're going to do is we're going to fit the model. So history equals DNN model dot fit, train features, comma, train labels, comma, validation split equals 0.2, but I want my validation split to be 1. Verbose equals 0, epochs equals 100, and then you can see the CPU times and the wall times. And then I'm gonna have to rerun this, but I'm not gonna rerun it right now. Now we're going to make predictions. Val predictions equals DNN model dot predict val features dot flatten. And then now we're inserting code to print the predicted values and the actual values onto a graph. And so A equals PLT.axis, aspect equals equal, PLT.scatter, val labels equals val predictions, PLT X label, true values, MPG, PLT.Y label, predictions.MPG, limbs equals 0 to 50, PLT.X limbs is limbs, PLT.Y limbs, and then an underscore equals PLT.plot limbs. And so there you go. There's your graph where you can see the predicted values, which is the straight line across the actual values, which is the dots. And so now we're going to calculate the RMSE, which is root mean squared error. That is a goodness of fit measurement, and the RMSE is 3. And then now what we're going to do is we're going to go create a data frame so you can compare the actual values against the predicted values. And you can see that the actual values against the predicted values is not that bad. Okay, so now you can see the errors. This is just something that TensorFlow did so you can see the errors if you want. And so now what it says is it says save model, and so DNN.save DNN model, and then you can reload the model if you want to, but I've never done that. This is the first. I've got limited experience in saving models and reloading them, and then whenever I tried to it was really called features reload or something like that, and it didn't work, so I changed it. So, but I have limited experience in saving models and reloading them. But that's it. That is it for this code review. And I'm going to rerun the code review because I found the mistake that because I like to have 90% of a training data set and 10% of a validation data set. And on one of the points on the fit, I didn't do that. So I can try to run it, but I think it's going to take a while to run it. So I'm going to run it outside of this video, but you've seen for yourself that I changed it from 0.2 to 0.1. But it depends on what you like. If you want 80% training and 20% validation, you can have that. It's up to you what you want. I just prefer to have 90% training and 10% validation. So I'm going to conclude this video because I've covered the code review. I did actually get the data set and the code from the TensorFlow website, but I did actually make some modifications to it to suit my needs. So I hope you like that. And I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And thank you very much for watching my code review. I look forward to making more code reviews for you in the future.